This is Antenna Group with Jeannie, Anthony, and Tyler. The objective of this experiment is to determine the resonant frequency using the Marconi ground plate antenna. Once the resonant frequency is found, steps toward finding the near and far field can happen. The relationship between signal and strength should be noted to further understand how the distance between two antennas affects the overall signal strength. Lastly, a loop antenna should be designed to show polarization.
Heinrich Hertz was born in Hamburg, Germany in 1857. He had a real love for mathematics and physics. After getting out of the military, he pursued a scientific curriculum at the University of Munich. A few years after he married, he began his historic train of events leading to his opening of the radio spectrum and his vindication of Maxwell's theory. Hertz's experiment was to demonstrate the existence of electromagnetic waves. To do so, he had a powerful induction coil to excite his primary conductor and a micrometer-driven spark gap at the terminals of a loop. The way Hertz found resonance was by adjusting the perimeter of a loop and graphing his data. We found resonance with the use of an oscilloscope. Hertz also had to create his own frequency. We were able to use a function generator to create our frequency. This experiment helped us to find the near field and the far field.
This is our antenna moving from far field to near field. In theory, as we move forward, the wave should get bigger until we enter the near field, which is less than 3 meters. The wave is getting slightly bigger, and then it gets a lot bigger when we enter the near field.
The equations shown below are related to the antenna experiment. The frequency and their wavelength are related to the antennas because the lower the frequency, then the longer the wavelength. Since antennas emit and absorb radio waves, the greater the wavelength, the further the antennas can be from each other. The near field is 1d cubed, and the far field is 1d squared, which helps find the resonant frequency. To find the power, you take the voltage peak to peak and square it, and then divide it by the resistance, which in this case is 1 kilo ohm.
In theory, an antenna's resonance is made up of a magnetic field brought by an inductor and an electric field brought by a capacitor. In general, the larger antenna, the lower the resonant frequency will be. It should also be noted that if the antenna being tested is exactly half the wavelength, then the equivalent circuit will resonate. For our experiment, we used 2 Marconi ground plate vertical antennas, one for receiving and one for transmitting. In a Marconi antenna, the center conductor is connected to the vertical radiator and the shield is connected to the earth ground. The earth acts as a mirror and provides the other wavelength of the antenna, which makes it equivalent to a vertical dipole, resulting in a vertical polarized omnidirection antenna. It should lastly be noted that the dropping radials technique will be used to adjust the antenna's impedance to around 5 ohms. The loop antenna used was a resonant loop governed by the intended wavelength of operation. Thus, they are typically used at higher frequencies. They can also be viewed as folded dipole deformed into a different shape and have rather similar characteristics such as high radiation efficiency.
The materials used in this experiment include 2 ground plane vertical antennas, 1 loop antenna, 2 oscilloscopes and leads, 1 10-mA RF generator, styrofoam, tape, a flash drive, 1 kilo ohm resistor, and 2 portable cards.
This is our transmitting antenna. It is modeled after Marconi's ground antenna. I have the oscilloscope leads and our function generator down here, the high-powered function generator. And I'm going to hook up the leads to the antenna. And I'm going to hook up channel 1 and channel 2 to ground, which is this plate down here. And then I'm going to hook up, after this, to the 1 kilo ohm resistor. And this one's also going to go to the 1 kilo ohm resistor into ground. Lastly, you're going to take the function generator and we're going to hook it up also to the ground and the 1 kilo ohm resistor. From there, you can adjust your function generator and your oscilloscope to give you a good resonant frequency around 83 to like 90 megahertz.
This is our receiving antenna, also modeled after Marconi. We have our channel 1 leading from the oscilloscope, hooks up here, and it hooks up to a wire leading to the ground plate. which is right here. We can adjust this cart backwards or forwards, adjusting the distance between the transmitting and receiving antennas. And that helps us determine our relationship between signal and distance.
From here we can find the polarization of this loop. To do so, if we move it vertically, the signal becomes very choppy, and if we move it horizontally, it'll become clean. And there we have found the polarization of this loop.
The screenshots show the progression of the wavelengths in the distance. We start at 3 meters and continue all the way to 21 meters. The resonant frequency is around 82 megahertz at each distance. The relationship between the voltage peak to peak and the distance is shown in the graph along with the calculated power. Power was calculated by squaring the voltage and then dividing it by the resistance, which is 1.
Some errors that occurred through this process of this lab was a 60 Hz interference, which was a numerous amount of things from the lights on the ceiling to the power grid from computers. We also encountered a signal interruption whenever a person walked in between the two antennas. This is our signal with no interference, and this is what happens when we get a signal interference. It gets very noisy. If given more time, we found a design for an AM detector. This would allow us to send sound from the transmitter to the receiver antenna.
This experiment tested the skills of finding a resonant frequency between the two Marconi antennas. We related the varying distances, moving the antennas closer or farther away to the voltage peak to peak seen in the oscilloscope. The loop design aspect of the experiment proved to be the most difficult due to finding a proper method to increase or decrease the gap without interfering with the signal. Overall, our experiment proved to further justify Hertz's experiment by finding the resonant frequency between our two antennas.